So here's the proof for the power rule for differentiation, that x to the n differentiates to n times x to the n minus 1. Before we go into the proof, a few things we have to talk about first. One is Pascal's triangle. This is triangle right here. Right, the first row is 1, then you got 1, 1, 1, 2, 1, 1, 3, 3, 1. I apologize for the markups. But basically the pattern to this triangle is that each number is the sum of the two numbers above it. So like 4 is 1 plus 3. 15 is 5 plus 10. 6 is 5 plus 1. That's how you make the triangle. Named for Blaise Pascal, a French mathematician from the 1600s, but it had been known by Indian mathematicians for at least 1,000 years before Pascal was even born. That, it turns out, is related to something called combinations. Combinations are a topic in math called combinatorics, which is counting, like counting how many ways there are to like pick bagels from a bagel shop or to flip coins, or how many ways there are to do things. And combinations are actually what these numbers are. Like this symbol right here means 0, choose 0. That's 1, choose 0. 1, choose 1. That's 3, choose 1. And these numbers in the triangle end up being combinations. Right? So again, combinations are a topic in counting, when you count how many ways there are to do something. And this triangle just happens to be all combinations. So for example, this row right here is 3, choose 0, 3, choose 1, 3, choose 2, 3, choose 3. Those are all the combinations. Which means this is like 5, choose 0, 5, choose 1, 5, choose 2, 5, choose 3, etc. And like how you would see that is if like you went to like a cookie shop and they had 5 kinds of cookies and you're going to pick 3, there are 5 choose ways of doing it. So there's 10 ways to do it. But anyways, that gives us the binomial theorem. The binomial theorem allows us to multiply out a binomial. So a 2-term expression raised to the nth power. So x plus y to the nth power is n choose 0, x to the n, y to the 0, n choose 1, x to the n minus 1, y, n choose 2, x to the n minus 2, y squared. And the pattern is as the power of x goes up, as the pattern of the power of x goes down, the power of y goes up. So let me just give you an example, because it'll be easy to see when I do it act. Let's do like x plus y to the 4th power. That would be tough to do by hand, having to multiply it all out, but that just uses the 4th row of Pascal's triangle. This is the 0th row, 1st row, 2nd row, 3rd row, 4th row. And so the first coefficient is 1, x to the 4th, y to the 0th. Then it's 4, x cubed, y to the 1st. Then 6, x squared, y squared. Then 4, x to the 1st, y cubed. And then 1, x to the 0th, y to the 4th. So I was able to multiply out that binomial super easily using combinations and the binomial theorem and Pascal's triangle. And you can see the power of x goes down, the power of y goes up. Okay, so now that we have those two things down, let's check out the proof of this rule. So the derivative with respect to x of x to the n equals the limit as delta x goes to 0 of x plus delta x to the n power minus x to the n over delta x. That's the definition of the derivative. We use the binomial theorem to expand this binomial, x plus delta x to the n power. So it starts off as n choose 0, x to the n, plus n choose 1, x to the n minus 1 delta x, n choose 2, x to the n minus 2 delta x squared, etc., until the last term, and then minus x to the n power. So there's more terms to the expansion, but I just kind of put plus dot 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 to stand for them. And then minus x to the n, all over delta x. N choose 0 is 1, so that's just 1x to the n. N choose 1 is n. n choose 2 is dependent on n, so we don't know what that one equals yet. Likewise, all the other terms, we don't know what they are exactly, but the first two we know. So all we did there was n choose 0 is 1, n choose 1 is n, and the other terms we don't know. But we don't need to, because first these cancel out, the x to the n's. Once they cancel out, every term up here has a delta x, so one delta x will cancel off from all of them, and so on down the line. And what you'll be left with is n x to the n minus 1 plus n choose 2 x n minus 2 delta x to the first, all the way to the very last term, which is n choose n delta x to the n minus 1. Right, and this delta x on bottom canceled out. And now it's okay to plug in 0 for delta x, because we no longer divide by 0. And when you do that, all of these terms have at least one power of delta x. Which means when you plug in 0, they all cancel out, leaving you with just n times x to the n minus 1. So that is the proof of this. This only actually works for positive whole numbers of n. Once we learn about logarithms, we can prove this for any real number n. But still, that is the proof of the power rule. Any questions about that? Shoot me an email or stop by office hours, because it is, as every proof is, kind of hard to follow.